Okay, so now we're going to talk about Morse-Smale functions. And the basic idea behind these are that we would like the situation where we can just look at the stable manifolds of the of the critical points, and then think of them as being forming a complex, basically, right? Um, and so, first, to understand how you do that, it's helpful to understand when it might fail to have this sort of complex property. Okay, so the stable manifolds do not necessarily form a complex. Okay, and so in particular, it's like the part of the properties where it fails is the following. So specifically, right, it is possible that the boundary of a stable manifold is not itself a stable manifold of a lower dimension. Okay. It's not the union of stable manifolds of lower dimension. And then the example of this is this upright torus as before. Okay, so if you have an upright torus, okay, and in particular you have these sort of two critical points, W, which is the top of the saddle, if you will, and let's call that V, right? Then so the stable one manifold right? So the stable one manifold of the top saddle goes down to the bottom saddle, right? W reaches down to the lower saddle. V, okay. So, so in particular, the boundary of that one-dimensional stable manifold, it's like it includes a point V, right? So the boundary of that one manifold, right, contains V, but that is not a zero stable manifold. Not a stable zero manifold. Okay. So and you know, it's like, so the net reason for this is in some sense that you have now an integral curve which starts and ends at a saddle. So this is a consequence of having integral curves or integral lines that start and end at saddles. Okay. And another way to think about this is that to see the problem, is that the stable one manifold of W, right, which is this line, right, is the unstable one manifold of this lower saddle V. Okay, and then the point is that generically, right, these stable and unstable manifolds do not intersect, right, generically. So the stable and unstable manifolds do not intersect. Okay, right. And in fact, if they, yeah, all right. Well, they, they can intersect, but they have to intersect transversely, right? Well, maybe I should say that generically, this does not happen, right? Okay, all right. So now we're able to sort of define for you what are called Morse-Smale functions, which have this genericity property. Okay. Okay. So definition. All right. A Morse-Smale function is a Morse function f, which is a map from M to the reals, right, whose stable and unstable manifolds intersect only transversely. Okay, so the problem isn't so much just that they intersect, but they intersect in a way that, it's like the tangent space at the intersections to each of those manifolds agree with each other. Okay, right. Okay, so let me try to again give you a rough idea what one means. It's like by intersecting transversely. So roughly, right. This requires that the stable and unstable manifolds cross. And they intersect. Okay, so imagine you have one stable manifold and another, and you have an unstable manifold which crosses this, right? You Oh, this is maybe a hard picture. Okay, well, maybe let's just look at it this way, right? Okay, so you have an intersection point, you have the tangent space associated with one, and you have the tangent space associated with the other, right? And basically the intersection of those tangent spaces has to be just a single point, right? So that's what means by transversal. So let's try to be more precise about this. Okay. So let's see we have sigma, which is a map from RQ to the manifold, and it's like nu is RP to the manifold. Okay, and these are smooth maps. Okay, so if you have a point Z in M, which is in the common image, right? So there's an intersection to these two things, right? We say that sigma and nu intersect transversally, right? If the sort of the tangent spaces of these things, right? So you take the linearization of the map, okay, okay, at a point x, okay, so x is going to have the property that it maps to this common point z, right? So sigma of x is going to be z, right? Okay, times the tangent space at x of this space, right? So the linearization, it's like gives you a map from tangent spaces to tangent spaces. So the sigma x is a map from t. Okay, so my notation is that the x is here, right? So tx, it's like rq to t sigma x m, but t sigma x is z, so this is just t z m, right? Okay. So, all right. So in any case, so this thing here, right, is contained in TZM, and then you can look at the sum of this, sort of similar thing with the second map, right? But now you have a point y, T nu y, T y r p. Okay, this is again, it's like part of TCM. Okay, and then we have that nu of y is equal to z. Right, so we want these two things, it's like together to span the entire tangent space TZM. Okay, so it's not to say that, you know, so depending on the dimension, it's like the manifolds which intersect, it's not to say that, you know, it's like they can't, I guess the precise statement is not to say that they can't have a situation where the intersection of the tangent spaces is just a point, but it has to be that the span, it's like of those two tangent spaces together, it's like spans the entire tangent space in M. Okay. All right. So so we say that and I guess I should say that in this picture here, right, where you have you're sort of trying to visualize something which is in 3 dimensions, and you have a 2-dimensional manifold intersecting with a 1-dimensional manifold, right? Then that notion of transversality has to basically mean it's like that intersection is is just the origin, right? Okay. And that's because, yeah, that's because it's like this is one-dimensional, this is two-dimensional together. In the best case, it's like the span can only be at most 3 dimensions, and then you have to subtract off it's like the intersection dimension, right, in order to figure out what the dimension of the span is. Okay. Yeah. So anyway, so we say that sigma and nu, right, are transversal. To each other if they intersect transversally at every point in their common image. Okay. All right. So, all right. So, and again, it's like, so the way you're going to think about this is that this sigma and nu then are going to be essentially this, if you will, it's like a parametrization. It's like of the, you know, the stable and unstable manifolds which you see from before, right? And again, it's like they have to intersect in such a way that they, you know, it's like that the tangent sort of spaces, it's like which they generate at their point of intersection, it's like spans the entire tangent space, it's like of the manifold. Okay. All right. And so the claim then is that if you then have this sort of Morse function, which also has this sort of Morse-Smale property, it's like that the stable and unstable manifolds intersect transversely, then you're in a situation where just looking at the stable manifolds of the Morse-Smale function, right, is going to give you a way to construct a complex on the manifold. Right. So let me stop here.